one, I spent a lot of time and studying a lot, I got a B. But count two, I passed by 70%. And literally all the
minimum solutions and find the largest x.
And so I spent the whole semester just like trying to get
to the
that yesterday, and it was the worst.
Yeah.
I was feeling it for the last week.
Right. Well, you guys are lucky because I had to take yesterday off because I had an upset stomach, so I had to take the entire day off and it was miserable. But I recovered quick enough that I did not have to take any time off today. Yay. Not that I did not enjoy like a day off. My cats were nursing me, so it was kind of fun. Both cats. All right, so let's go ahead and get back to where we left off. Okay, so the key idea of the lecture last time, even though we were kind of all caught up in the details of how do we use an N-channel MOSFET as opposed to a P-channel MOSFET, which way, what is the right orientation, which side is the source, which side is the drain, and stuff like that. The bottom line is we can implement a NAND gate using transistors. Okay, we took something, we took devices out of the physical world. Okay, you can buy transistors, right? And turn it into a logic gate, which is something that is it performs a logical operation. It's equivalent to a logical operator in C and C++. And somebody may say, but we don't have a NAND operator in C and C++, but that's okay, because we found a way to make other gates using the NAND gate. We found a way to make a NOT gate out of a NAND gate. We found a way to make an AND gate, non-negated AND gate, using NAND gates. And we also found a way to make an OR gate out of NAND gates. And that's the significance of last lecture. The last lecture basically connects the physical world, physical devices, to operations, logical operations, Boolean operations that we have to perform when we are doing programming. Okay? So the details is, yeah, it's a little messy and you have to look up a few things to understand, transistors and stuff like that. But the overall idea is we have that connection now. Okay? So this is not going to be the first time that I will mention the three types of questions. The first question is how, okay? Which tend to be messy because it has to do with low-level details. Okay, this is like looking at things from a microscope. Okay, the next level up is what? Okay, instead of looking at something using a microscope and you have no idea of the thing itself, now you actually get to see the entire thing. That's the what question. What is this? And then the next level up is why. Okay, now not from a philosophical perspective, because computer science is a very pragmatic field, compared to some other fields. So when we ask why, we are asking, well, what purpose does it serve? Okay? And the why question is missed a lot in textbooks and whatnot, but it is very important because it helps you connect a concept to other concepts that you might have understood already. The more connections you draw between the concepts, the better you can understand other concepts and the less you have to memorize things. Okay, so that's why I try my best to remember to kind of look at things at three different levels. Okay, the how, okay, the circuitry of the P and N channel MOSFETs, that's the how. Okay, how are they connected? How does a MOSFET or transistor behave and stuff like that? That's the how. The what is the NAND 2 gate. Okay, if you give it 1, 1 as input, it will give you a 0 as the output. If you give it anything else, it will give you a 1 as the output. That's the what. The why is, hey, now we have a way to use transistors to implement any logic, any Boolean operators that you need to implement. Are there any questions about these three aspects of a topic? Questions? Okay, all right. So we are continuing with that particular topic, so we'll go back and continue with this. You guys saw some really interesting pictures down there. Okay, so keep going. There we go. So this starts with a discussion of values, numbers, and representation of numbers. And I have a picture of the Seven Samurai, which is an anime movie, I guess it's an OVA, to basically show you the difference between values and numbers. Okay? Can someone count or double check the number of, I guess, people, characters in this picture? There are 7, okay? If I show this picture to someone who does not speak English at all, do you think that person will still understand the concept of the quantity 7? Yes, and that person will probably tell me the value 7 in some other language, in some other representation. Is that okay? All right. So why do we need 7? Why do we have this symbol? What is the purpose?
Representation of a number.
It's a representation of a number. Okay, very good. What if I tell you that this symbol, in my mind, represents 7? Would that be useful at all in a class? No, because none of you shares this meaning with me, right? So it has no meaning. This has no meaning to you. But this does, because everybody in this class better understand that this symbol represents the quantity of 7. Is that okay? What if I were to tell you this also means 7?
You have to explain.
Okay, so we'll get to that. Okay, we'll get to that somewhere in this slide here. But this really is another representation of the same quantity which we normally use this symbol to represent. Okay, for those of you who know kanji or Chinese characters, this is 7. Okay, what about in Spanish? What is 7? How do you spell it?
S-I-E-T-E.
S-I-E-T-E. Okay? So that's also representing the quantity of 7. Russian has 7. Japanese has 7, which I think might be the same character. Okay? Vietnamese has the concept of 7 as a quantity. So all of these, okay, are really just different representations of the same quantity. Now, some of these are traditionally, it's cultural, okay? This evolves from pictograms, okay? So it has a particular pathway of how it evolved into this. This probably has its own history of, why, this, spelling, became, how 7 is represented by this spelling. Do you know how that came along? No? So at some point, that story is lost, right? That's okay. That is okay. We don't even understand why this is representing 7 either, right? So that's okay. But in this class, we will know why this is representing 7. And why binary numbers is a better way to do things all around. Okay. All right. So that's why we have this picture here. And the same thing here, okay? This is an expression. We can call this a smiley face, a happy face, and so on. But the words happy, the words smiley, they are representations. The emotion that you're getting out of interpreting this picture is a sensation. It is not. It's wordless. Okay. When we put a word to it, we're just representing it so that we can communicate with somebody else. Okay. Somebody's on the phone. They're asking you, okay, so what is your teacher showing you in class, right? Now these days, this example won't work anymore because you guys can Snapchat, take a picture and go like, yeah, this is what he's showing us. But before Snapchatting and cameras and stuff like that, you can tell your friend, oh, he's showing us a smiley face. That's a representation. Okay. All right. And the words representing happy, I just picked Chinese. I think this is Russian. This is Japanese, Vietnamese, Spanish, and so on. Now, if I miss your language, it's not because I do not value your culture It's just that there's a certain number of things that I can do in class. I cannot research all the possible cultures. So there's no intention of ignoring any particular culture. All right, so let's talk about Bayes conversion. Every time I talk about Bayes conversion, some of you may get bored because you have taken classes from me before and we have talked about Bayes conversion before. But every time I talk about Bayes conversion, I am amazed that people do not understand that they already understand Bayes conversion. Okay. Who thinks that you are qualified to work at a McDonald's even when their register is not working? So somebody gives you X amount of money, like say $20, and you have to give that person a change of $11.98. Can you do that without the machine telling you what kind of bills and what kind of coins and how many of those to give to the customer? You can do that, right? Okay, so let's figure that out. $11.98, okay, which is exactly the number that I mentioned earlier, okay? So using only the common bills and the common coins, okay, how would you do this? I don't want to hear 1,198 pennies. Okay? Because that would be a very easy way to do it, but it's not pragmatic, okay? So how would you do this? Where do you start? From here or from here? From the larger part, okay? So you say, oh, $11.98. What is the largest bill that is representing the value of less than or equal to what I need? That's the question that you're asking, right? And what is the answer to that? $10. $10. Very good. So you say, I need one $10 bill, okay? And you are left with $1.98. Okay, easy peasy, right? $1 bill. Took care of that one here. You got 98 cents left. This is where things go really weird in US currency. Because in 98 cents, you don't say 9 dimes. You say 3/4. Okay, so you have 3 times 25 cents, and then you have what, 23 cents left. Okay, so with 23 cents, you have 2 dimes, and then 3 pennies. Okay. So before I gave you the entire solution, how many people worked this out way before I got everything wrote down, written on the board? And you tell me that you don't know how to do Bayes conversion? No, seriously. If you know how to do this, you are already better than doing Bayes conversion, okay? Because I want you to look at the lack of regularity of the multiplier of the currency system that we use, okay? The coins and the bills, okay? We start with a penny, right? Then we go to a nickel, and we go to a dime. I know we have half dollars, but those are not common. So we go to a quarter, but we don't have half dollars. We have $1 bills, we have $5 bills, $10 bills. We have a $2 bill in between, but those are rare as well, so we don't count those. Then we have 20 and then 50. Okay. Tell me what is regular about these. Look at the multiplier between the values, okay? We have a multiplier of 5 between these two. We have a multiplier of 2 between these two. We have a multiplier of 2.5 between these two. Then we switch to a 4. Then we switch to a 5. Then we switch back to a 2. Then we switch back to we do another 2. And then we go for another 2.5. There's no regularity whatsoever. And yet you can handle it. Well, that kind of confirms me that people are irrational. Because the more rational things are, the harder it is. The more irrational it is, the easier it is. Doesn't make sense to me. Okay, so let's work out another example. So this time we got $19, and I have to think of a way, one that works out with these numbers. 75 cents. Okay, that will work. Okay, but this time I want everything in binary. Binary. What does that mean? Twos, right? Okay. So in a binary system, we start with the dollar bill, okay? And the next one up is a $2 bill. The next one up is $4 bill, $8 bills, $16 bills, $32 bills, and so on. Do you see the pattern here? Everything is just twice the one before. Regularity, lack of regularity. Rational, irrational. Okay? We can go backwards too. We can have half-dollar coins. We can have quarter-dollar coins. And if you want, we can have $8 bills. 1, 2, 5, $8 coins. Okay? That's fine. And you can go all the way, you know, if you want 16th, 32nd, and so on, that's okay too. Okay? But do you see how these values are related in a very rigid and regular way? They're off by twice. They're twice, okay? Twice of this, twice of that, twice of that, half of this, half of this, half of this. Is that okay? So, using this particular system, how do I come up with this value? Using the least number of bills and coins. How would you work it out? Okay, we start with 32. Okay, well, too much. Next one down is 16, right? Okay, so 16, that will drop us down to $3.75. Okay, so you go like, maybe 2 do this. Okay, so we have $1.75 left. 1 would do it. Okay, so now we have 75 cents left. Look down this list. A $half would do. And now we have 25 cents left. So we take another 25 cents and we're done. I think it's easier. No? You don't think so? It's just, it's a habit kind of thing, okay? But we have just worked out the binary number. If I were to write this out as a binary number, what do you think it's going to look like? We got 116, no 8, no 4, 1, 2, 1, 1. And here's the binary point. I don't call it a decimal point anymore. It's a binary point. We got 1/2, 1/4, no 8s. That's a binary number. Any questions about this? But do you see how this is actually easier from the perspective of applying logic compared to this, which has no regularity? You have to remember, you know, 5 follows 1, 10 follows 5, 25 follows 10, and so on. Whereas this one, there's no memorization needed because they're all powers of 2. But the way you work out how to represent a value is the same way. The value is 116, 1, 2, 1, 1, 1/2, and 1/4. Add that up, and that's the value that I want. Over here, we got 1/10, 1, 1, 3/4, 2/10, and 3/100. And that adds up to the value that we want. Is that okay? All right, so one more thing, okay? So this example is not exactly the same as the one in the notes, but it's close, okay? So if you read the notes, you will get the same exercise, okay? But the next thing we want to do is to take a look at how numbers are represented, okay? So I'll do it on the whiteboard. Let's see. I will try this, see if it works this semester, because sometimes it works and sometimes it doesn't work. I'm going to try this out. It's a document camera, so it will allow me to write something on a piece of paper and be able to display that on the projector. So we'll give it a try. For those of you who were in 440 last semester, did it work okay or not? It worked okay? All right, so we'll we'll give it a try. I broke off the LED light last semester, so I had to glue it back. The camera did not come with its own LED light, so I had to use an epoxy putty to glue it on. Whatever material they used to make the USB extender, the L-shaped thing, does not glue very well with epoxy. One of the few material that epoxy doesn't glue well. Okay, so this has to go to an extension like that. Yep, it's lighting up. I need to find the stand. That. And makes you wonder what else is in my bag. All I can say, nothing illegal. Unlike some other professors, who I would not name. I think I've used them all the pages, but that's okay. I just need something that's blank on one side. Okay, there we go. How many people know VLC? Okay, but VLC can be used this way too. It's really useful for many different purposes, but it can be used for this purpose. There we go. So I need the orientation to be right. So okay, just need to move this over here. Uh-oh. Yep, I think I just lost oh, okay. Connectivity issues. So I might need to restart the whole thing. Do it one more time. Ah. Okay, I see. So, okay, I want it to be in landscape orientation. Better cord management. Okay. So I do want it to rotate. Perfect. Okay. So this is correct. Okay, very good. All right. And of course, now I have forgotten what I was preparing to present. Oh, right, okay. Numbers, how numbers are represented, how values are represented as numbers. Okay, so, it's something that is already kind of on the whiteboard, but I just want to kind of make it more obvious, okay? So let's consider this number here. Okay? And it's base 10, okay, so there's no trick with the base here. So 407.2 is the number. I want to know what it is representing. And you guys would say, well, any elementary school student can figure that out because it is 407.2, okay, and 2/10, okay? But why is that, okay? So this is where, elementary school students may not be able to answer as well, because this is 4 times 100 plus 0 times 10 plus 7 times 1 plus 2 times 0.1. Is that making any sense? Yeah, but this doesn't belong in college. Then I'll go to the next step and say, hey, 100 is 10 to the power of 2, 10 is 10 to the power of 1, 1 is 10 to the power of 0, and 0.1 is 10 to the power of -1. How about that? So do you see any pattern here? Every digit is representing the quantity of a particular power of 10 in this case, because this is a base 10 number. Is that making any sense? Okay. So that means binary numbers are no more and no less in terms of, is it difficult? Is it not difficult? It's no different. So let's pick out the value on the whiteboard right now. It's 10011.11, okay? As a base 2 number, I use a subscript 2 to indicate this is actually a binary number. Okay, I may not have enough space to spread it out sideways, so I'm going to have to stack it up vertically. Okay, so with this number, what is the value it is representing? So we can start with this 1 here. Okay, so we have 1 times 1 plus, then we look at this 1 here. It is 1 times 2 plus, we have 0 times 4. 0 times 8, because this is 8, and then 1 times 16. On the other side, we have the powers to the negative, so we have 1 times 1/2, and then we have 1 times 1/4. Okay? But we can rewrite everything as a power of 2. So we can start with, let's start with the 16. Okay, so we have 1 times 2 to the power of 4, plus 0 times 2 to the power of 3, which is the 8, plus 0 times 2 to the power of 2, which is the 4, plus 1 times 2 to the power of 1, which is the 2, plus 1 times 2 to the power of 0, which is the 1 here. And then on the fractional side, oops, there we go. On the fractional side, we have 1 times 2 to the power of -1, which is the half, and then plus 1 times 2 to the power of -2, which is the quarter. It is very systematic. Each digit is representing the quantity of a power of 2 in this case, because we are dealing with a binary representation. Is that okay? So binary numbers, decimal numbers, it really does not make a difference, because we are still writing the numbers the same way. The most significant digit, or the ones representing the higher quantities, is on the left-hand side. The ones that are representing the lower quantities are on the right-hand side. Is that okay? All right. So given this is the case, we can now conclude and say that, yep, we know binary numbers. Okay, we know how to represent values using binary numbers. We can interpret the binary number and figure out what value it is representing. Are there any questions about base conversion? No questions? Okay, well, if you don't have any questions, I'm going to ask you something. Yep.
So for non-decimal numbers, you can get odd numbers by using the base number 1. But for decimals, how would you get odd decimals, I guess?
Odd decimals.
Yeah, like 0.76.
0.76 and use do it in binary.
Yeah.
You end up with a infinite recurring pattern, just like 1 divided by 3 in decimal is 0.3333 and so on. So you end up with some values like that in any base. Yeah. But it's a recurring pattern. Okay, that's a good question. All right, so if you guys don't have any questions, I'm going to ask you a few questions. So we'll start with the conversion of some numbers. Okay, see if you guys can do the conversion relatively quickly. Okay, so let's do 195. Okay, 195 converted into base 2. I'll give you guys, I don't know, 2 minutes. You can use a computer to do it, but only in the way that you are writing the program to do it. Okay, so maybe a few more seconds. Okay, so let's go ahead and figure out this answer. There are 2 ways to do it, by the way, or 2 ways that I know of that are pretty easy. One is to divide it by 2 and keep dividing it until you get zeros, okay? So if you divide 195 by 2, you get 97 with a remainder of 1. Divide 97 by 2, you get 48 with a remainder of 1. Divide 48 by 2, you get 24 with a remainder of 0. Divide 24 by 2, you get 12 with a remainder of 0. Divide 12 by 2, you get 6 with a remainder of 0. Divide 6 by 2, you get 3 with a remainder of 0. Divide 3 by 2, you get 1 with a remainder of 1. And that's when you stop, because 1 divided by 2 is 0 with a remainder of 1, and that pattern will keep going. So when you do it this way, this becomes the most significant bit, and this becomes the least significant bit, which means the number is 11000011. It just so happens to look exactly the same no matter which way you spell it. Okay, but the way to do it is to go from here. Okay, this is one way to do it. The other way to do this is to look at 195, and you pick out the largest power of 2 that is less than or equal to this value, which is 128. Okay, so you say, yep, there's 128 in it, and then you look at the remaining portion, which is 67. So you look at 67, and then once again you use the largest power of 2 that is less than or equal to 67, which is 64. Then you have 3 left. Then you look at 3. You look at the largest power of 2 that is less than or equal to 3, which is 2. And then you end up with a 1, and you do exactly the same thing. The largest power of 2 that is less than or equal to 1 is 1. So now you're done. Okay? Then you look at all the values. You look at 128, 64, 2, and 1. And then the way you do this is you, if it's 1, it is just 1 itself with no zeros after that. If it's a 2, it's a 1 0. If it's 64, which is 2 to the power of 6, right? Then you have 1 followed by 6 zeros. 1, 2, 3, 4, 5, 6. And then 128 is 1 followed by 7 zeros. Then you add up all these, then you end up with 1, 1, 0, 0, 0, 0, 1, 1. Oh. There you go. So you end up with exactly the same representation. So you can either use the compare and subtract method, or you can use the division method, depending on whether you can do division by 2 really fast, or whether you can do subtraction really fast. So it depends on that's your preference. Are there any questions about converting from base 10 to base 2? Yep.
I was a little confused on the first way you did it, when you had a 1 for when you did the 2 divided by 27.
You mean this one? You mean this
the
one?
Next to it, right? I guess I'm just missing something. Like, how, I guess on that example, how do you know when to put a 1 and when to put a 0?
That's a remainder of a division.
Oh.
So in this case, 195 divided by 2 is 97 with a remainder of 1.
Oh, okay, with 1 remainder.
Yep. And because you're dividing by 2, the remainder can only be a 0 or a 1. Okay, all right. So now that we know how to convert from any value into base 2, what about computation using base 2? Why are we interested in base 2, by the way?
Computer language.
It's computer related, okay? But why do you think computers like binary numbers?
Because the logic gates can only accept 2 values.
Because the logic gate, deals with, only 2 values as input, 1 or 0, true or false, okay? And why do you think that is the case? Do we have to have, binary digital computers? Well, no, we can actually have analog computers, but they're far more expensive because the transistors of a non-binary digital computer, the transistors have to be of high consistency. Okay, whereas a binary computer, because it's either on or off, if you're off by a little bit, it's okay. Okay, it will still be close enough to be considered a 1, and then the next gate doesn't even care because once this gate interprets this input as a 1 and then come up with an output, the error does not they don't stack up, they don't add up. Okay, with an analog computer, every single component would add up, so it will start to distort the computation as you have artifacts and whatnot in the chain of computation. But binary numbers, binary representation doesn't have that problem. It's either there or not. Okay, so you do have a large margin of error when it comes to, well, this is kind of close to a 1, I'll take it as a 1, okay? All right, so that's why we are interested in binary numbers. But the question now is, can we do all the things that we normally do with binary numbers, just like the way we do it with base 10? And the answer is yes, absolutely. So this part here is just a repetition of what we talked about a little bit earlier, except I chose a different value. Okay, same thing over here, 101, 111, 101, 110 is representing the value of 46, but basically the same idea, okay? So I'm not going to repeat all of that stuff. So we are jumping all the way to adding, okay? Adding numbers in binary, okay? So I don't want you guys to read this, okay? So let me flip this to something else, okay? When you were learning addition, or if you know anyone who's young and just about to learn addition at this point, okay? Was that an easy process? Now you know addition, you think it's easy, right? But back when you were learning to add using base 10 numbers, was that easy? How do you know 6 plus 7 is 3 with a carry of 1? How do you know that? Think back in those days. Memorization, exactly. It is all memorization. Because I'm pretty sure some of you still remember, when you learn addition in class, your teacher would give you a block that has 6 units. The teacher will give you another block that has 7 units, right? And then you stack these two together, and then you have a block that has 10 units. So now you can say, hey, this cannot be represented by anything less than 10, but it has 10 and then 3 remaining after the 10. That's how you learn that 6 plus 7 is 3 with a carry of 1. The concept of carry is very important because it allows you to do multi-digit addition. Is that okay? So how many of those pairs do you have to remember? That 8 plus 5 is also 3 with a carry of 1. 9 plus 4 is 3 with a carry of 1, and so on. That table is pretty big, wasn't it? It's easy to make a mistake. Let's figure out how many unique things you have to memorize. Okay? So you have a table. Okay? This pen is fading out. Okay. So you have a table. It goes from 0 to 9 on one side, 0 to 9 to the other side. Addition is symmetric, so you only have to remember half the table. Okay, so the other half is just a mirror image. No problem. 0 plus whatever is just 0. Okay, forget about the first column. You still have this many items to remember, which is approximately what? 49, 48. And the more complex ones are the ones with a carry, okay? But even the ones without carry, you still have to memorize. 5 plus 2 is 7. How do you know that? You have memorized it. Is that okay? So you have 40-something unique things to memorize, and that's just for addition. Subtraction has its own table. Multiplication has its own table. Division is based on multiplication, but it doesn't have a table. So you have to master all of these tables, perform all of these memorizations in order to do arithmetics, in order to add, subtract, multiply, and divide. What if I were to tell you your teacher could have done something differently that would have made your days so much easier? Okay, so 20 years too late, I'm going to tell you this, okay? Base 2 is the answer. I mean, seriously, base 2 is the answer. If I show this to a third grader, they would not have gone back to base 10, ever. Okay, base 10 is like for the old generation. You know, base 2 is the way to go. In base 2, what is 0 plus 0? I got nothing, and I'm adding nothing to nothing. How much do I have now? Nothing. Does it depend on the base? No. 0 plus 1? 1. Does it depend on the base? 1 plus 0? Doesn't depend on the base. The only one that is tricky, because we're coming from base 10, is 1 plus 1. 1 plus 1 is special because I cannot use a single digit in base 2 to represent the quantity of 2. Because I only have which 2 digits? 1 or 0. I cannot use either one to represent a 2. So I would say this is a 0, but with a carry of 1, because a digit cannot represent that value anymore. It's the same thing as dealing with 5 plus 5 in base 10. 5 plus 5 has a quantity that you cannot use a single digit in base 10 to represent. So what do? You have a carry of 1 and say that, well, I cannot represent it, but the next guy can help. Is that okay? That's pretty easy. So all of the other ones basically just implicitly have a carry of 0. What about subtraction? 0 minus 0 is 0. Are you sure that works in base 2? I take away nothing from nothing. Do I end up with nothing? Pretty sure. Okay. What about 1 minus 0? I got one thing, and somebody came and took nothing out of it. How much do I have left? 1. Okay, very good. I got one thing to begin with. Someone came and took it away. I got nothing left. The only one that's tricky is this one. 0 minus 1. I got nothing. Somebody took 1 away. So what do I do? Well, fortunately, there's a bank next to me. So I say, hey, can I lend 2? can I borrow 2? So once I borrow 2, I got 2 in my pocket, and then this bully came and say, well, you haven't paid me the 1 for today. Okay, here's your 1. I got 1 left. But now I have a borrow. Is that the same concept as the borrow concept in base 10 subtraction? It's the same thing as 1 minus 3 in base 10. It's an 8 with a borrow of 1. You only have one thing. Somebody came and say, I want 3 of those. You say, I don't have enough to give you 1. No, I don't have. You only have 1. Somebody came and asked for 3, and you say, I don't have 3. I only got 1. So you borrow 1 from the next digit. But in base 10, when you borrow, you're always borrowing 10 more than the unit of yours, right? So you're borrowing 10 combined with the 1 that you have now. After borrowing, you have 11. Take away the 3, you have 8 left. Same concept in base 2, except when you borrow, you're borrowing twice the quantity that your digit is representing. That's it. But forget about memorizing 40-something in the table for addition. You only really got one thing to remember because the other 3 are really obvious. Same thing for subtraction. Is that making any sense or not? Because what you need to do, if you're looking at this thing and go like, wow, this is way too much, you have to draw the parallel between base 2 and base 10, because the idea of carrying and the idea of borrowing is still exactly the same. It's just the quantity that you are borrowing and the quantity that you're carrying is no longer 10, it is now 2. That's the only difference. Is that okay? All right. So if that is okay, I'm going to switch back to this note here and go through some examples. Okay, this is a good one. I'm just going to copy and paste it because I don't want to scroll up so that you guys can see the actual answer. So I'm going to copy and paste it here. There we go. There we go. Okay, so now we can work this out. Okay, so the way we work out multi-digit subtraction or addition in this case is kind of like this. Okay, so let me see. Okay, and there we go. What is 1 minus 1? 1 minus 1. Well, you can look up this table. You can kind of. This is open book, open notes, open whiteboard. There you go. 1 plus 1 is 0 with a carry. Now, so I put a carry on this separate row here. Okay, this is kind of like my notation because I want to separate the result of the addition from the carry of the addition. So I break it up into 2 halves. Okay. All right. So for the first column, what is 0 plus 0? 0 plus 0 is just a 0. Okay. All right. Now we are working on the second column, which is bit 1 of the addition. 1 plus 1 is 0 with a carry. 0 plus 1 is a 1. Okay, very good. 1 plus 0 is a 1. 1 plus 1 is a 0 with a carry. 0 plus 1 is a 1. 1 plus 1 is a 0 with a carry. 0 plus 0 is a 0. 0 plus 1 is a 1. And neither addition ends up with a carry. So the carry over here is going to be a 0. 1 plus 0 is a 1. 1 plus 0 is a 1. Neither addition ends up with a carry. So the carry to the next digit is a 0. 0 plus 1 is a 1. 1 plus 0 is a 1. Neither addition ends up with a carry. 0 plus 0 is a 0. 0 plus 0 is a 0. So that's the binary addition example. Well, I can do anything on the whiteboard and make a mistake in the process. How do you check that I did not make a mistake? How do you do a quick checksum and say, well, does this number make sense? How about we convert both numbers to base 10, perform the addition in base 10, and check whether the sum in base 10 matches the sum of the binary number. Okay? Easy way to double check and also exercise base conversion at the same time. Okay, so we look at this number and we try to figure out what it is. So the most significant one is a 32 because it's 2 to the power of 5. So we have a 32 plus 111 is 7, so I'm cheating here by short-circuiting it a little bit here. So it's 39 is the first number. The second number starts with a 64. 64 plus an 8 plus a 3. So that is a 75, I think. Does it look like a 75? Yeah, looks that way. Okay, so the sum, I'm just doing a base conversion of the sum, and then we will do the double checking by adding the numbers in decimal. So this is 7 times 16 plus 2. 7 times 16 is 112. Plus 2 is 114. Okay, so do they match? I mean, if I add up the decimal numbers, do they come up with the same value? Okay, now this is not 100% validation of my binary addition because I can make several mistakes and have those mistakes masking each other. Okay, but the likelihood of that happening is pretty slim. So I'm, let's say, 95% sure that the calculation was done correctly. Okay? But if you really want to double check, just use a calculator. I'm pretty sure most of your scientific calculators has a binary mode. So use the binary mode, do the addition, and then convert the number back to base 10. You can double check really quickly and make sure that I did not make a mistake in the process. But is the process itself okay? Does everybody understand the process? Okay, all right. If you do not quite understand the entire process, it's okay because it is all documented here. So there's a step-by-step documentation. Well, I lied because after the third slide, I got bored and I just jumped to the answer. But let's double check because this is the actual answer, 0111 0010, and that's the same answer. So I'm fairly sure that that's the right answer. Is that okay? All right. Shall we do subtraction? Okay, let's do subtraction. So once again, I'm going to use the example. Okay. Well, the example is really the reverse of what we start off with, so we can do a little bit better. Okay? I think we can use an example that is not a part of this, so we can just come up with a number. And I intentionally try to end up with a borrow at the end. Okay, so this is what I want to work with. And I use one row just for the borrow. So this row here is the borrow. So I'm going to use a B to indicate this row is indicating the borrow bits. And it starts with a 0 because this is the least significant column. And there's nothing that can possibly borrow out of this column. And that's why we start with a 0 at that position. All right, so we'll start with this one. What is 0 minus 1? Okay, so look at the table here. 0 minus 1 is 1 with a borrow. So we put a 1 here, which is the result of the subtraction, but it also ends up with a borrow. Then we have another subtraction, which is this 1 minus this 0, which is the borrow from, quote-unquote, borrow from a less significant column. 0 minus 1 is a 1. Okay? 0 minus 0 is a 0. 0 minus 1 is a 1, once again with a borrow. 1 minus 1 is a 0. 0 minus 1 is a 1 with a borrow. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 1 minus 1 is a 0 with no borrow in both subtractions. 1 minus 0 is a 1. Oops. There we go. 1 minus 0 is a 1. Neither generate a borrow of 1. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with a final borrow of 1 that does not fit in the answer, because the answer to binary subtraction or binary addition has to be of exactly the same width as the numbers that are given to you. So if the numbers are 8 bits, the answer has to be 8 bit. So if I need more digits to represent the answer, sorry, can't do that. But I do remember that I end up with a final borrow, which basically means, hey, we have an extra borrow here. If I could borrow, then this is the answer. So we just end up with an extra borrow. Yep, question?
Yeah, so
Yep.
I don't know how to point this out. Go ahead. To the second to last
Column.
column. So it's 1 minus 0 and you get a 1, right?
Yep.
But then how does that carry over? How does that multiply?
You mean this 0 minus
The
this
left
one?
side, the left.
Oh, you mean this one?
Yeah.
0 minus 1 is ends up with a borrow and also a result of 1. Because according to this table, 0 minus 1 is 1 with a borrow. Which is kind of the same thing as 1 minus 3 in base 10 is an 8 with a borrow. Is that okay?
And then the remaining one.
The remaining one, which is the extra borrow, you mean this one here? Yeah, this is an extra borrow. It basically just means that the second number is larger than the first number. You're trying to subtract more than what you have. So you end up with an extra borrow in this case because there's not enough to give to the first number.
With a 0 minus 1. The 0 minus 1. Or the, yeah.
Yeah, it's an extra borrow from the next power of 2. But it cannot be recorded as a part of the answer. Yep.
So one is the binary number would be the negative sign?
No, that's a slightly different thing. So we'll get to how negative numbers or negative values are represented, but it's not this way. Okay, but that's a good question. Okay, but how do we double check that this calculation is actually correct? So let's go ahead and figure it out. Okay, so this is 3 times 16 plus 4, which is 52, and this one here is 4 times 16 plus 5, that's 69. Okay, so 52 minus 69. Now this value, okay, so we'll go ahead and do the base conversion first of 11101111. Okay, that is 15 times 16 plus 15. Whoops, nope, 14 times 16, and that is what? Well, I guess I can do it the other way around, which is 255 minus 16. That's, my arithmetic really sucks. I think it's 239. Is that right?
Yes.
Yeah. Okay, so it's 239. Okay. So it doesn't seem to make any sense at all. You know, how can we have 52 minus 69 being 239? Well, it's 239, but remember, we are borrowing from the next power of 2. Okay? Okay, so let's go back to this picture and ask, but what exactly does that mean? That extra 1 means, oh, we ended up borrowing something that cannot be represented. But which power of 2 are we borrowing from? Okay, let's count, okay? Power 2 to the power of 0, to the power of 1, 2, 3, 4, 5, 6, 7. This is 2 to the power of 8. In other words, we just borrowed a 2 to the power of 8 to finish the subtraction. What is 2 to the power of 8? 256. Okay, so the actual value that we are representing is 256 minus 239 because this is what we borrowed. And this is what we have left after the subtraction. What is 256 minus 239? 17, okay.
Isn't it 239 minus 256?
Yes, correct. Because we owe 256. Thank you. So it's negative 17. And what about this subtraction? What is 52 minus 69? Negative 17. So they do match. Okay, we just have to take that one extra borrow into consideration because this is what I have left in my wallet, which is the same as 239. But this is what I owe the bank, which is 256. So if someone is to assess my worth, it would be how much money I have in my wallet minus how much I owe the bank, which is negative 17. So my net worth is negative $17 in this case. Because I had $52 in my pocket and I just bought something that's worth that is priced at $69. But it makes sense. Everything makes sense. Okay? How did I pay for that money? How did I pay for that worth? But are you guys okay with the binary subtraction, binary addition? At least in concept. I know the details need some practice, so I can give you guys some practice. You can practice, okay? Some calculators have a random number generator. Okay, does yours have a random number generator? No? Okay, this is what I'm going to show you. Okay, so forget about calculators. Who would use a calculator in a class like this? We got spreadsheets. Are you kidding me? Spreadsheets, man. Okay, so with spreadsheets, you can use random number generator, and this is just using the Google spreadsheet. So with a random between, you can generate a number between two values, okay? However, whichever range you want to use. So let's just say that you don't want to deal with 8-bit numbers because it's too long, too much to deal with. Stick with 4-bit numbers, okay? So you're dealing with 0 to 15 in that case, okay? So go from 0 to 15 as one number, and just say, okay, I want the next one to be a number within the same range, okay? Then you can convert these into binary numbers, okay? There's a function to do the binary conversion too. So it's dec2bin, and specify that cell, and then you can do the same thing over here. Dec2bin over here. There you go. So now you can easily generate numbers as starting points. So let's say you're dealing with addition, okay? So how do you deal with addition in this case? So let me insert one more column to the left. There we go. Okay, so if you're doing addition, you can do something like this. You can easily say, I just want the sum of these two numbers. Okay, so we just add this number to this number. We have 26. And you can also just say, well, let's convert that into binary numbers. But you can see how this one has an extra one here. That extra one is your carry of what? The leftover carry. Okay? You can do subtraction also. Yep?
So when we add two binaries, we can have an answer which is longer than.
Yes,
both.
but but that's a carry. Okay.
Yeah.
Now, if you want to use the way that we do things here, then what you want to do is not to use not to just use an addition. You want to basically do a mod function. So you want to do a mod of this with 16, and then the carry, which I can put here. Okay. So the carry is whether this value or the sum of these two is more than 16 or not. Okay. So you can. Okay, I'm just trying to figure out what is the quickest way to do it. Ceiling. No. Floor. Okay, there we go. you can use the floor function of this number plus this number, and then the whole thing divided by 16. There we go. So this is the carry. Okay. Okay, let's take a look at the function here. Okay, so this is just regular arithmetics. Okay, when do you need a carry? If you're only dealing with 4-bit numbers, when do you have a final carry of 1? When the sum cannot be represented by a 4-bit number. Okay, you say, well, I'm only given 4-bit numbers, I cannot represent this quantity. I can represent up to a certain amount of it, but then there will be one more that belongs to the next significant digit that has to take care of it. Is that okay? That's what the 1 is. So with a 4-bit number, you can only represent 0 to 15, right? So when you divide the number, which is the sum of B1 and B2 by 16, if it ends up with 1 or 1 point something, that means the sum is at least 16, which means you have a borrow. I use a floor function here just to make it look clean so that it is just 1 instead of 1 point something.
And 16 is 2 to the power of 4? 4, yeah?
2, yeah, 16 is 2 to the power 4.
4-bit numbers.
So that's why we have 4-bit numbers, correct. Yep, that's right. And you can make these, you can force these to use exactly 4 bits, just in case, so you end up with leading zeros if you end up with some other values. And with this, you can go to tools, and I think there's a way to automatically regenerate the random numbers. So I think there's a way to refresh. Okay, how do we refresh the data? Or just recompute? Calculate. F9, there we go. Okay, so look at the screen, don't blink. Ah, it doesn't work. Maybe I have to put it on the cell that can recompute. There we go. So if you put it on the cell or the cells that can recompute, oh, okay, that works. That works. Okay, it has to be on an individual basis, so it's kind of lame that way. But you can use the random generator to basically, just give you different exercises to play with. The other thing you can also do is to copy and paste it a few times, because then it will use a different set of numbers. There we go. Is that okay so far? Sort of. Okay, we got about 10 minutes left, and I'm glad that we have at least 10 minutes left, because I want to go through the connection to the next topic. Okay, and you can do about the same thing with subtraction. In fact, okay, this is what I'll do. Okay, I don't have it now, but during lab time today or after lab time, maybe sometime tomorrow, I will give you a Google spreadsheet in the shared folder for this class. So you will have a spreadsheet where you can play with different examples. Then you can exercise how to do binary addition, how to do binary subtraction, and so on. How does that sound? But I'm not going to grade it, because obviously things can be double checked, and you can fix your own errors or notice your own mistakes. So I'm not going to grade it, but I will give you a tool so that you can practice it. Okay? All right. So I do want to go to the next slide, because it is actually important for me to at least make that connection today. Okay, we may not be able to get through all the details, but I want to make the connection. So with this slide, okay, I'm just repeating all the same old stuff here. 0 plus 0 is 0 with a carry of 0, blah, 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 blah. Okay, all the same stuff that is already captured here in green on the whiteboard. Okay, nothing new. But what I want to do is to make a new notation and say the result of 0 plus 0 is 0. The result of 0 plus 1 is 1. The result of 1 plus 0 is 1. The result of 1 plus 1 is 1. If 1 plus 1 is 0. The carry of 0 plus 0 is 0. The result of carry 0 plus 1 is 0. The carry of 1 plus 0 is 0. The carry of 1 plus 1 is 1. And for borrow, the only case where you have a 1 is when you subtract 1 from 0, then you have a borrow. For all the other cases, you have a borrow of 0. In other words, up to this point, I'm just changing the notation, but they mean exactly the same thing as what we have in this table. Is that okay? Just changing the notation, using some symbols and functions to denote these things. Are we good? Okay? I know how much you guys like the transistors and logic gates. So we're going to bridge the concept of addition and subtraction to logic gates. Yep, go ahead.
About the borrow of the third one, 1 and 0, it's 0. And on the board it says that 1 and 0 is 0.
Okay. 0 minus 1 is the one with a borrow of 1. And this is saying 0 minus, whoops.
The third one.
How did I do that? Okay, there we go. The third one, this one?
Right.
1 minus 0 is a 1 with no borrow. B is borrow. Okay? Alright. So I'm gonna make the bridge. Okay, we got about 6 minutes left, and that's what I need to bridge the gap. Okay? To bridge the gap, the easiest one to look at is the carry. So when you look at the carry function, 0 blah 0 is 0, 0 blah 1 is 0, 1 blah 0 is 0, 1 blah 1 is 1. Okay, what can that blah possibly be? It's some logical AND. Okay? Wait, do we know how to do an AND? In fact, we know how to do it using transistors, because we can boil an AND gate down to NAND gates, and we already know how to make a NAND gate out of 4 transistors. Okay? Well, what about the other ones? Maybe this is just coincidental and it's easy to do it. What about borrow? I bet you cannot use a single gate to do borrow. And the answer is right. I cannot use a single gate to do borrow. I need 2 logic gates to do it. Okay? Because I can negate the first input and keep the second one and put a conjunction. Okay, so if you scroll down here, okay, this is, oops, I can't, there we go. This is how we can do the borrow function, but using only logical operations, Boolean operations, logical not x and y. Okay, those are the mathematical symbols for negation and conjunction. Okay. What about the other one? What about the result? Okay, this one seems to be harder because we have 2 cases where the result is a 1 and 2 cases where the result is 0. So when you look at the result, okay, it is over here. It's a little bit longer, but still doable. Okay, because what we do is we negate x and then conjunction, and y, the whole thing, or x and the negation of y, the whole thing. That's how we can get the same results. But the bottom line is, this is the how. Okay, this is really low level. This is the nitty-gritty detail. This is the how. But when we take a step back, it means that we can now convert arithmetic rules into operations only involving Boolean operators. But we already know that all the Boolean operators that we already know can be done by the NAND gate. And then we also know that the NAND gate can be made out of 4 transistors. It may not be optimized. Okay, you may be wasting transistors, but we can now perform multi-digit addition and subtraction using transistors. I'm not going to ask you guys to give me a circuit that works, okay? But in terms of concept, we can now do it. So that's the last concept I really want to convey in today's class, because it ties in everything that we have already talked about. Everything from transistors to logic gates. Now we can do arithmetic operations, at least addition and subtraction with binary numbers. But binary numbers are just binary numbers. It's not as good as base 10 numbers. It's better, exactly, okay? Because with base 10 numbers, there's no way we can use transistors to do it. There's no way we can use binary operations to do it. But because we're dealing with base 2 numbers, it can all be done with Boolean operators. So that's the why, okay? The why of what we are talking about is we can now do everything using transistors, okay? At least addition and subtraction at this point, okay? Now, we haven't really talked about how to group things so that we can do multi-digit addition and multi-digit subtraction. That's what I want you guys to read for this weekend, is to read here, okay? So, but that's only half the operation. So read this part, read carry repo, and also read carry look ahead, okay? So finish this, whole slide here, and if you need to go back to the previous slides, you go ahead and review those. All of these are linked from Moodle, okay, in this particular order. So if you go to Moodle, yep, go ahead.
I was just wondering, what's the name of the collection notes for this particular?
It's on the title bar. It is called binary addition and subtraction as Boolean operations. I can show you the top part here. The problem is, the title bar, you guys cannot see the title bar at all, because of the way they arrange the screen here. But I think it's still linked from inside the topic in Moodle that we are currently in. Yep. All right. So we are running out of time today. I hope you guys have a nice weekend. Just kind of keep an eye on these things. One more thing, since we have 2 minutes left. Okay. So with this class, okay, I'm not sure about the other classes, so I cannot speak for the other classes. With this class, I always compare studying for this class as a slow cooker. Okay. So how do you make a really delicious cuisine out of a slow cooker? You start with good ingredients, right? So you put good ingredients into a slow cooker, and then you turn it on, and then what do? You wait, you give it time, right? And then occasionally you go back to the pot, you taste it, you go like, well, I can use a little more salt, right? I can use a little more spice, and then you close the lid and just let it cook. That's how you can study for this class, is you study, you get all the information in, but you don't try to understand everything in the fullest degree the first time, okay? You don't stare at the notes, you don't try to memorize the notes. The worst you can do in this class is to read the notes enough times that you can recite it. That is not a good sign, okay? So you want to read it, get the gist of it, understand a part of it, and then let your brain, let your mind cook it. Because your subconscious is more powerful than you think it is, okay? If you have the right ingredients, your subconscious will make the connections most of the time. Okay, just come back to it and check on it once in a while, and then go back and do something else. Okay?
Is there a lab today?
There's lab today. It's the same thing that we did on the other day. So if you got it done already, there's no need to go. Or if you have questions about today's lecture, I can answer those questions in the lab as well.
I had a question about the lecture. Probably, but just this.